Yes, this is how we got started. So this first paper was in flat space, but now, like, I think this is the latest paper that was published about clocks, that was published in 2023. There we can now, since we managed to, let's say, generalize our techniques to include curved spacetime. It sounds simple, but literally it took us more than 15 years to be able to do that. And we're using quantum field theory in curved spacetime. So then we finally had some, theoretical methodologies that allow us to address that question. And what we did is, like, we looked at a clock, a light clock, but we now were able to describe the clock in the space-time of the Earth, treating the space-time of the Earth like with the Schwarzschild metric, and come up with a model of a clock and discuss how the clock ticks, and, talk about the Schwarzschild radius of the Earth and how does this show up in the face of the clock, and so on. So that was like,
interesting.
We then came up with a notion of clock time already. In this clock, at each slice within the clock, the proper time is different. And we said, okay, but you could still build a clock by looking at the collective oscillations. And that gave me an idea that, okay, now maybe we can go back to the atoms and redefine the notion of the clock time using the collective oscillations and so on. But this is a student of mine is working on that. And we don't, we're just starting. Like, we don't really have much to say about the atomic case yet.
All right.
Okay, so now the last thing I want to talk about with respect to these experiments is mass. So, I was telling you how Roger proposed many years ago that if you have a massive superposition, this is unstable. And he argued that by showing that there was a conflict between the superposition principle and the equivalence principle. So he said, yes, you could have a superposition of a massive system that, for him, this would already be quantum gravity, because you have a gravitational field in a superposition of two different configurations, but these are unstable and they decay very quickly. And that is why we don't see superposition in the classical world. So what kind of masses would you need to, in order to see if the predictions of Roger are correct or not?
Do you mind briefly outlining why is it that the superposition contradicts the equivalence principle or the strong equivalence principle?
Yes. So he starts by describing a mass that is in a superposition that is falling. And then he says, okay, if you describe the situation from a Newtonian point of view, and he writes like the wave function, and now from an Einsteinian point of view, and he writes like a different equation. So he says these wave functions have to be the same up to a phase. No, because in quantum theory, states, wave functions are equivalent up to a phase. So, but you see, his whole argument, I'm going to show you a paper that I wrote with Roger in the next slide. And in that paper, we write an introduction where we go through Roger's arguments, but they're not necessarily simple. And one of the reasons why is because we don't have a theory for that. So Roger makes arguments that are like good arguments, well informed, but without actually having a theory. So sometimes the arguments are talking about quantum field theory and curved spacetime, and then he might make a Newtonian approximation and so on. But he shows that the Einsteinian point of view is different from the Newtonian point of view, and that there is a contradiction there, and that then because of that, he argues that these superpositions should be short-lived. And he goes beyond that because he gives you a formula that measures sort of the error. And this gives you an energy uncertainty. And it's related to the gravitational self-energy of the difference in the superposition. So you take some, maybe that is maybe going more technical, but we can if you want to, because I know that your followers are quite well educated in physics. So let me jump and then I come back a little bit here.
Sure.
This is the paper that I mentioned that I wrote with Roger. And what we did in this paper is that we calculated, how massive would these superpositions had to be if we used the Bose-Einstein condensate. I'm going to come back to that. But we found that you need at least something like 10 to the 9 atoms in a superposition. And let me tell you where the field is now. So, people started to put electrons in a superposition of two different locations using like a double slit experiment. I don't know, maybe
Sure.
90 years ago. I don't remember when was the first experiment with electrons. And from there, they said, okay, it works for electrons. Amazing. Let's do it now with atoms. And, then it's like, how bigger can the states, the system gets? And the record is held by Markus Arndt's group in the University of Vienna as well, where he has been able to put big molecules in a superposition. And by big, I mean the molecules have around 2,000 atoms.
Wow.
But for gravity to act, you need at least 10 to the 9. Actually, for molecules, you need even more. So you can see we're very far from that.
What do you mean for gravity to act? I thought the assumption is that gravity acts as long as you have mass. Don't these have masses?
Yes, but these are stable superpositions. No, they.
Oh, according to the calculation from Penrose?
Yes, Marcus showed that you can have these superpositions, and I think they lasted milliseconds. I don't exactly remember how long he had them for. So they are stable for that long in the lab. So gravity is not causing the collapse of superpositions at those scales.
I see.
But now the question is Roger right? Because if Roger is right, then that explains why we don't see superpositions in the macroscopic world. And what would be super interesting is to see that, that is a big open question in fundamental quantum mechanics, is to understand what takes you from quantum states being in superpositions to the classical world where we don't see quantum superpositions. It's a very interesting question. Marcus and many other people are trying to address this question in an experimental point of view from the experiment by trying to put more mass into the superpositions. There are many different experiments going on at the moment, and they use, for example, nanoparticles, nanobeads made of silicon or silicia, diamonds, little mirrors, rods, even membranes. There's many experiments going on. And also a record has been held by Markus Aspenmeier, also in Vienna. So I spent 3 years in Vienna because of these amazing people and experiments there. So I was very lucky to get a visiting professorship for that long and be in the same environment where these amazing scientists are. And so Marcus was able to bring one of these nanobeads to the quantum regime by cooling it down to lower vibrational states. So they're already in the quantum, let's say, scales, but with 10 to the 8 atomic masses, so quite a big bead, but he cannot put them yet into a superposition of two different locations. That has not been possible. Also, one of my colleagues I'm in Southampton, so one of my colleagues there, Hendrik Ulbrich, also has a very recent amazing paper where he takes these little beads and he manages to measure gravity. But this is all classical. But anyway, I mean, at those scales where quantum starts to kick in, well, what he wants to do is push these experiments so that maybe he sees some quantum gravity. Still far from that, but let's say approaching. But this is where things are at with respect to the experiments with big mass. So what I did with Roger is that when he started to tell me about his proposal and the experiments that people were doing, I noticed that all of these experiments were using solids, no? Mirrors, beads, and so on. And it's very difficult to cool a solid to the to very cold temperatures where you have little noise. So they haven't been able to make more progress because of the noise, because you can't cool them enough. Now, a Bose-Einstein condensate is a really beautiful system. I think it's my favorite system because you can reach half a nanokelvin, like the coldest things that we can do. And you can get up to 10 to the atoms. I mean, that's not very common, but there's been an experiment using hydrogen in which they cool 10 to the 10 atoms into a condensate. So let me tell you a little bit what a condensate is. So you have let's say, when you learn quantum mechanics, you learn that if you put a particle in a potential, well, the particle is there moving in the potential. But if you cool it to the ground state, it will, let's say, if you manage to the ground state, the atom will be completely delocalized within the potential. So you don't know what the position of the atom is in that whole thing. No, that's really, I don't know, when I did that in quantum mechanics, I loved it. Now think about having 10 to the 8, 10 to the 10 atoms all cool down. But atoms are bosons, so they can all occupy the same quantum state. So you can cool them all down to the ground state. And that is what is called a Bose-Einstein condensate. So you have the biggest system that behaves in a quantum mechanical way. And like I said, in the experiment, people have been able to cool these systems to half a nanokelvin.
Right.
So I was wondering if then this would be a good system to test Roger's predictions. And that's what we did together. We said, okay, how would it go with a Bose-Einstein condensate? And also super complicated because you would have to create a superposition of all the atoms on the left with all the atoms on the right. And although the temperatures are that low, people have not been able to create these superpositions. They're called noon states because you have N, 0, 0, N.
Yes, no? Cool.
And you know what? The record is by one of my colleagues called Chris Westbrook, and he's been able to do 2 atoms. And so you can have many, you can have up to 10 to the, you can have many atoms in quantum states in a Bose-Einstein condensate, but not many atoms in a spatial superposition of 2 different space locations. That's where gravity acts. So this is what I now have been working on in the last 2 years. And well, it's not related to, it's inspired by this work with Roger, but it's a complete new thing. I hope I can talk about it at a later time with you. But in that previous paper with Roger, we studied things like Roger had given formulas for uniform spheres, and in a BC you could have pancakes or elongated BCs with different distributions of the density, and we studied if these would enhance the effects predicted by Roger. And then, well, you have a lot of losses, and we studied the losses and so on. And that's how we came up with this. Well, with a BC, you need at least 10 to the 9 particles, maybe even 10 to the 10, in order to start being able to actually verify that the energy uncertainty of gravitational origin that Roger predicts has an effect.